So this year I've been tinkering with ranks for the first time, and I just want to tell you about the stuff I've been working on. So let's begin. Oop. So here's your standard slide on elliptic curves. Hopefully nothing new on this slide for you. We're going to take K a field, characteristic 0, just because that's all we'll need. An elliptic curve over a field K is a nice, smooth, projected, geometrically reducible curve defined over K as genus 1 with a distinguished point O, a rational point. And of course, using Riemann-Roch, you can choose a Weierstrass. So you can do E as inside P2, given by y squared equals fx, fx being a separable cubic polynomial. You might want to write that polynomial as x cubed plus ax plus b, but we'll have different shapes, so I'll just write it as a separable cubic. And that's the affine model. There's one point missing, which is the point O at infinity. And there's a group law on the K rational points, which hopefully you know. And I have some pictures here just taken from Wikipedia. And so on the first picture is really what you need to know is if you have E and Q and you connect with a line, you get a third point. And with the group law, these 3 points add up to 0. And that's basically the idea. If P equals Q, you take the tangent line and you'll intersect at a third point. And from this, you get the group law. And, yeah. So just pause in case people are coming in, but this is your standard group law. Of course, what's really nice is if you have 2 K rational points, this method produces a third. And now let's talk about number fields. For an elliptic curve over a number field K, we have the Mordell-Weil theorem, and that's that the set of K rational points of E is a finitely generated abelian group. So there's a finite number of rational points such that by doing this chord and tangent process, you can produce everything. And since it's finitely generated, it has an explicit structure as a group, a finite abelian group plus some free part over the integers. And the rank of that finally generated abelian group, that's the rank of our elliptic curve, which I'm just here denoting by the rank of E. Okay, so that's all the background I need so far. We have elliptic curves over number fields. Their Mordell-Weil group is finitely generated, and I'm interested today in ranks. So here are some big open questions, all well beyond what we could possibly prove. First one, given a number field, what ranks occur? What are the possible ranks that arise? Special case, still very hard. What ranks, well, are the ranks bounded? If we consider all elliptic curves over a fixed number field, are they bounded? Of course, if we increase the number field, we can make the ranks bigger and bigger, but for a fixed number field, are they bounded? When K is Q, the largest known rank is 29. And this is a question where the common folklore belief has flip-flopped now a couple times. And the third big open question is, suppose you understand what ranks occur, you could ask about their distribution. And just the coarsest kind of distribution you could ask is, are there infinitely many elliptic curves of a given rank? Okay, so these are just very hard questions about ranks. Just let this sit for a moment, but and so here's what I want to talk about today, the following theorem. So for any number field K, an integer from 0 up to 4 R, there are infinitely many elliptic curves over K of rank exactly R. So you give me your favorite number field, you give me an integer between 0 and 4, I can produce infinitely many elliptic curves over that number field of that particular rank. And by infinitely many, I'm not meaning the model. I don't want you changing the model and say that's a new elliptic curve. Of course, I mean up to isomorphism over K. And it's still, a theorem still true, even if you consider isomorphism over K bar. These aren't just twists of each other. These are legitimately geometrically different elliptic curves. And a very easy corollary is that for any number field K, an integer from 0 to 4, there is an elliptic curve over K in rank R. And up until this year, this would have only been known in the case R equals 0, which is kind of surprising because you sort of think half of elliptic curves over number field should have rank 1, and only this year have we been able to prove that for any number field there is an elliptic curve of rank. The corollary is not very interesting over Q, but for a general number field, even just the existence of these guys is new. Okay, so let's sit for a moment, but this is what I want to talk about today. This basic invariant of elliptic curve over number field to rank, and I can produce elliptic curves with small rank over any number field. So again, that's the theorem restated. And as far as I know, this theorem covers all cases in literature of a number field in R for which the statement of the theorem holds. So some earlier results. R equals 0 was done in a paper of Mazur-Rubin, 2010. They were working on Hilbert's 10th problem, and I don't think they were trying to prove it, but they just proved it, and someone pointed out that they proved it. That's my reckon. R equals 1 case was independently proven by Clemens and Pagano, and if you're watching this in the future, you can scroll down and look at their video, the video 252 in the series, the seminar. R equals 1 was also known in special cases. For example, when K is Q, you can use Heanger points to produce elliptic curves of exactly rank 1. R equals 2 and K equals Q I did earlier this year in February, and that's kind of how this all started. Okay, so, and maybe just a remark, because sometimes when I present this, people feel like this should be known, as they're used to hearing about high rank elliptic curves. But it's actually hard to find the exact rank infinitely often. So there's an example here at the bottom. There are infinitely many elliptic curves over Q of rank at least 19. That's due to Elkies. That's the largest we know. And the key word is at least. Of these infinitely many, we don't know what the ranks are. For each particular elliptic curve, we could compute the rank, but we don't know what the ranks are for. We don't know which rank occurs, and if any rank occurs infinitely often and which one. Okay, so that's kind of how it differs from previous things. A lot of results in literature about ranking rank at least an integer, and here we're trying to get it exactly. Now, the basic strategy for computing the rank is to separately find a lower bound and an upper bound. And if you're lucky, hopefully they agree. So the straightforward way to find a lower bound is just to find points. I have k rational points. I look at the group they generate. I consider its rank. That is a lower bound on the rank. Upper bounds are harder. Really, the only way I have of thinking about it is the Selma groups. So for a positive integer n greater than 1, we have the k rational points mod n. And this finite group, which if you know the torsion points of your elliptic curve will tell you the rank, it maps into this Selma group, which all you need to know for now is it's a finite computable group. And this gives an upper bound on the rank. And so we'll do some Selma groups soon. But one thing I'll mention now, kind of foreshadow, is compute Selma groups. You need information about the bad primes of your elliptic curve. So when you have these infinite supply elliptic curves I want to produce, I have to understand what the bad primes are in order to compute Selma groups, in order to compute upper bounds. Okay, so now I know there's some experts here, but let me kind of bore you for 5 minutes. Let me just talk about the very easiest kind of Selma groups, those arising from an isogeny of degree 2. So we're going to fix a field, and this will just set some notation we can use later too. So let's take a field of characteristic 0, have an elliptic curve over our field defined by this Weierstrass equation. If you look closely, it's not the usual Weierstrass equation. I have some extra powers of x going on there, a and b and k, and this number not equal to 0 to guarantee it's smooth. And this curve clearly has 1 point, 0, x equals 0, y equals 0, and that's a 2 torsion point. And what you can then do is take this elliptic curve and quotient out by the order 2 subgroup generated by 0, 0, and you get another elliptic curve. So this produces this isogeny I have here, E running from E to E prime, whose kernel is order 2 generated by 0, 0. And you can explicitly work out what it is. And I'll just say, you choose things appropriately. You can take this quotient elliptic curve to be defined by this other very explicit Weierstrass equation. And you can also look at, well, this also has a 0.00, which is 2 torsion, and you can do the same thing and quotient out again. And it turns out you'll get back the original elliptic curve, E. And this, I have this map, D hat, and this is just the dual of V. Okay, so we have an elliptic curve with a 2 torsion point. It gives the 2 torsion point gives this isogeny, and just we have explicit equations. It's very tangible. And so we have this exact sequence of groups. Don't worry about too much. The main thing is this blue group. That group knows the rank. You know the 2 torsion points of E. That blue group knows the rank. And I'm putting it in between these 2 other groups, which I want to study. And so all these are abelian groups, finite abelian groups, killed by 2. So I can view them as F2 vector spaces, and I can take the dimensions. And I get the dimension, I get the rank is equal to the dimension of the sum of the 2 dimensions of the spaces enclosing that blue group minus 2. There's some ambiguity in 2 torsion, but they all cancel out and I get this clean formula. So in particular, instead of that group I have in blue, I can look at these other 2 groups. E prime k mod the image of phi and ek mod the image of phi hat. And these 2 groups, if I can compute them, I will know the rank of the elliptic curve. Continuing my little just background on 2 descent. So at the top here, this is the only cohomology I think I have in this talk. So you have this short exact sequence given by phi. It's this isogeny from E to E prime with kernel generated by 0, 0. And you can then take the k-bar points and take the Galois invariants, and you get phi taking the k points of E to the k points of E prime, and then it maps by just cohomological things to an H1. The kernel is just a group of order 2 of a trivial Galois action. And I can identify that group with the non-zero square classes of k. And so then we have this delta E prime, this map that takes the k rational points of E prime as isogenous curve to non-zero square classes. And its kernel is exactly phi of ek. Okay, so that's our descent map. If you don't like that, there's a very easy explicit description in this case, because this is the most tangible case. If you take a point in k rational point of E prime, you take its x coordinate and you look at the square class you get. And that's basically the map. It doesn't work with the point at infinity, because you don't have an x coordinate, but it's a homomorphism, so it should take the point at infinity to 1. And when x is 0, when you have the point 0, 0, you can check that this is what you need to make this consistent with what's above. So it's just homomorphism defined cohomologically, but when you have equations, it's very concrete and computable. So we get this homomorphism, delta E prime, and it induces an injective homomorphism of this one of these 2 groups, which if I figure out their size, I'll know the rank, and it maps it injectively into the non-zero square classes. So it's taking this thing I don't know and mapping it to something I understand. It's not quite useful yet because it's taking something finite and mapping it into something infinite. So now we have our local conditions. So now we'll take a number field, and we have these 2 rows. The top is just with their number field k, and the bottom row, that's the same thing in construction we did, except now with the v-adic completion of k. And we get this commutative diagram where the map on the left is just an inclusion, because kv, the v-adic completion, is bigger. And the map on the right is just the standard quotient, because the square classes get bigger. And since it commutes, we can define this Selma group, which is just going to be the square classes. It consists of this elements square classes whose image, when you map down, lies in the image of the local points of that delta E prime. Okay, so it's kind of and so what we have, so this is the smallest group in the non-zero squared classes that contains the image just given these commutative diagrams. Okay, so we have one of these 2 groups we're trying to understand to get the rank. it maps into this Selma group, which is inside the square classes. And then what's nice about the Selma group is it's finite, so it actually gives a bound, and it's actually computable. You can put your elliptic curve into your computer, it will output the Selma group. For a finite place not dividing two with good reduction, the condition you're imposing, the image of this map, local map, is very straightforward. It's just the, well, I have it here. It's the element, it's the subgroup generated by the d-adic integers. That's at the good primes. The bad primes, the conditions are more complicated. And here's where I said, if you really want to compute a Selma group, you have to understand the bad primes. And so we have our injective homomorphism from our one group into the Selma group, and then switching the roles of E and E prime and phi dual, you get the second map into a different Selma group. And so our equation for the rank in terms of these two quotients of the k rational points of E prime and E, we can now get an upper bound in terms of the dimension of these Selma groups. And these Selma groups, I said, were computable, so this is a computable upper bound on the rank. So we have elliptic curves over number fields with a two torsion point. Lower bounds come by finding points. Upper bounds you can obtain by this particular Selma computation. I don't have any blinds, so hopefully things are okay. Okay, so that's our background. And now let's begin. So today I'm just going to focus on the rank 4 case. So we're going to kind of discuss some of the information that goes into proving their infinitely many elliptic curves of rank exactly 4. So I'm going to fix a number field and let E be the elliptic curve over the function field k adjoin t, just some parameter, defined by this equation, which I'm just pulling out of nowhere. Part of the talk is, as we go through, we'll see what kind of properties it has, and then you can figure out why I came up with this equation. The first right away amazing property is that it's discriminant, which is essentially the discriminant of the cubic in X. It's a polynomial in T, and it factors into linear terms, not what you would expect from a random Weierstrass equation. And so that T, I can start plugging numbers in my number field in for capital T, and that's always going to give me an elliptic curve, except when T is a root of this polynomial. So if I plug in a plus or minus 11, plus or minus 25, plus or minus 39, this is not going to give me a model of an elliptic curve. This curve has singular fibers, bad reduction above these points. The point at infinity is also good. And you can check that the plus or minus 25, those are fibers of additive reduction. The others are multiplicative. And there's a general bound, more of a geometric bound for the rank, which you can then use. And it tells that this particular elliptic curve, its kt points is at most 4. And the proof of this is just cohomology again, but it's more actual kind of geometric cohomology. Okay, so this is my elliptic curve. And the next slide, we have our elliptic curve. Its rank is at most 4. And in fact, this elliptic curve has rank exactly 4. And here's the structure of the Mordell-Weil group. So it has a point of order 2, that's 0, 0. And it has 4 other independent points. And here I wrote them down. You can check that these 4 points are independent on the curve. A little computation shows that actually they would generate the Mordell-Weil group here. Okay, and so now what I can do is I can take an element of K, but not in the set B. B were the ones where I plug in and I don't get a smooth model. I can plug in elements of K and I will get an elliptic curve defined over K. So just replace capital T, this parameter with little t, an element of K, and you get an elliptic curve. And an amazing theorem of Silverman, which is really just about heights, says that for all but finitely many t, specialization defines an injective homomorphism of the Mordell-Weil group of E over KT into the Mordell-Weil group of the specialization. And so in particular, for all but finitely many t, the rank of the specialization is at least 4. This is a way of producing elliptic curves of rank at least 4. I claim I want to produce ones of rank exactly 4, and so this is the lower bound, 4. summary again. For each element of k except the bad ones, we plug in t into my previous equation. I get a now elliptic curve defined over k. Its rank is at least 4, at least excluding a finitely many t. And you could ask what the rank actually is, and it's difficult, that's the talk, but there's sort of a minimalist conjecture, which is that the rank should be usually as small as it can be given the constraints we have. So in this case, the ranks are at least 4. And also there's the parity conjecture. The rank mod 2 should depend on the root number. So with this in mind, you would expect that the rank is 4 half the time and 5 half the time. And the goal in the rank 4 case is to find specializations for which the rank is exactly 4. So this is my supply of elliptic curves. Their rank at least 4. I need to somehow cleverly choose E to plug in to get rank exactly 4. So how to choose T? This slide is overwhelming, but main thing is there's no elliptic curves on this slide. We're going to make a bunch of choices which seem out of nowhere, but these will come up later. So we're just going to choose a set of non-zero prime ideals of OK, ring of integers of K, and let OKS be the ring of S integers. So I'm allowing negative valuation at primes at S.
Hi, David. Sorry, could I interrupt for
Yes,
a second? There's a question from Bjorn
sure.
in the chat and asking whether it's a theorem that the root number is split 50-50 for this particular family.
Um, it should be. I mean, I'm conjecturing it, so I can conjecture what I want. I'm not sure. It should be 50-50, but I'm not. It might be. I might need conjectures to get it to work.
Great. Thanks.
But I'm conjecturing, so I can conjecture what I like. But yeah, I think in this case it is a 50-50. At least numerically, it's 50-50. So great. So I had a set of S of prime ideals. And then for each set prime in that set, I'm fixing this open set UP of the p-adic completion of K, two copies of it. And for each infinite place, fixing a non-empty open subset UV of KV. So there's a bunch of choices. We'll deal with this. And now the following is kind of one of the engines of the proof. It's a consequence of a theorem of Chi, which generalizes work of Green, Tao, and Ziegler to number fields. And so it says there are non-zero M and N S integers such that the following hold. M plus En, it generates distinct prime ideals of this S integers as E for E in this set of bad fibers. These are elements of OKS and they're all prime and they're distinct. They generate distinct prime ideals. And these sets UP and UV, these are just conditions, constraints imposed on M and N. M and N lie in this open set, and M divided by N, it lies in this set UV for infinite places. So maybe it's a lot, but just when K is Q and S is empty, you have the infinite place. You can choose it to be the real numbers greater than 39. And all this above just says there are infinitely many integers, regular integers, so that m minus 39, m minus 25n, et cetera, up to m plus 39n are all just regular prime numbers. The condition u infinity is there just because when we think about prime numbers, usually we want them to be positive. So I'm forcing them to be positive. Okay. And of course, recall the Green-Tau theorem, there are arbitrary long arithmetic progressions in the primes. And this, what I have here, the special case would follow from Green-Tau. And so the thing in green and the stronger theorem of Chi, it's really just a Green-Tau theorem over number fields where I'm allowed to impose constraints, local conditions. So the big hammer, but it's letting me, it's basic, yes, it's Green-Tau theorem, but this very advanced number field version. I guess I titled this slide, How to Choose T, but there's no T here, so let me tell you. So here, the first thing is what I just said. There are non-zero S integers such that m plus En, all these guys just generate distinct prime ideals of this S integers. And with local conditions, which at this point we haven't said what they are. And now with such m and n, we can define our t, which is just going to be m divided by n. So that's going to be the numbers we want to plug into our elliptic curve. Yeah, specific elliptic curves. Why are we doing all this? Well, it's really this discriminant computation. When we plug in little t into our equation, we get this discriminant, which is here. I just replaced the capital T with a little t. And now I can plug in m over n, or t, and pull out all the n's. And I get this nice expression. And if I assume the set S contains all the primes that divide 2, 3, and 7, just because they're already dividing the discriminant, then the set of primes of OK for which the specialization at this particular t has bad reduction is a subset of S, this set I chose, and this other explicit set of primes, where here, if you look at m plus en and the prime ideal it generates in the S integers, it will come from a prime ideal of the regular OK, the regular ring of integers. What's going to happen. So you just look at this expression for the discriminant and see what primes divide it. And I have one comment. You might be worried about that giant power of n, I guess negative power. But it turns out if there's another prime that divides n, then this is getting closer and closer to a point at infinity where my model will have good reduction. So if a different prime divides little n, I can change my model and I'll actually have good reduction. And so that's really what this rigmarole is. I'm choosing t in such a way that I have specializations for which I understand exactly what the bad primes are. There's no, I know what the bad primes are. And if I know what the bad primes are, then I have a chance of actually computing Selma groups. And what happens at the primes in S? Well, you can choose the sets UP and impose whatever conditions you want. So kind of up to you. Okay, so this is kind of the way of choosing specializations using this generalization of green Tao to use specializations for my case, which I can actually understand the bad primes, and having the discriminant factor into linear terms was the key. Now let's go back to our Selma groups. So we plug in T, and now just like before, we have an isogeny because we have the 0, 0 point. And we define these two maps earlier. And now we actually have points, the two torsion point and these points from geometric points where I plug in T. So these are just the 4 points, independent points I had before, but now I'm plugging in little t. I'm suppressing the y coordinate because we don't need it. And it turns out here, I guess for space, I guess what 0, 0 doesn't give something new. So I have this image of delta ET, and it contains this group square classes. And when I look at for relations here, I can get rid of one of them. Can I? And it turns out that's as far as I can go. And so what I have is this image inside the Selma group, and I can check that its dimension is at least 3. I have the Selma group, and the points I know about give a subgroup of dimension 3 over F2. Okay, so we have this dimension at least 3, and a similar computation shows that the other Selma group has dimension at least 3. And so to prove that the rank is exactly 4, we just need to show that the dimensions are both exactly 3. Because our rank upper bound was these two dimensions added together. So 6 minus 2, which is 4. And then we would have a lower bound 4 and upper bound 4, and we'd have rank 4. And equivalently, we're showing the Selma groups are as small as possible given the known points for elliptic curves. Okay, and so now we have a lot of freedom here. This weird sets I chose, I can vary them. I can choose the set of primes ideals S, these open sets, these conditions I'm applying. I get to pick them, and hopefully I can choose them so that I can get my Selma groups to be small. That's the picture really, is we have this explicit elliptic curve family, the discriminant factors in the linear terms, using this generalization of green Tau to specialize, and I have freedom to actually sort of pick impose conditions. Okay. So there are local conditions. Let me just kind of give you a slide to hint at it. Again, the Selma group is inside the non-zero square classes, and it's cut out by these local images. For most prime ideals, this square classes, the p-adic ones will be a group of order 4. And here's sort of one way, just to give you a hint of how you can produce useful constraints to make your Selma group smaller. That if you have an E in this bad set, then for all but finitely primes, if T, an element of K status, it's the difference between T and E is p-adic valuation 1, then this gives the dimension of the local constraint. The first case is 4. That's kind of boring. That's saying that there's no local constraint at all. It's the full square class of non-zero square classes of KP. The bottom one, when it's 1, that's actually very strong. That's saying it's doing as much constraining as possible. And then 1 and 2 is in the middle somewhere. And so these are conditions. So you can choose your set S and impose conditions to kind of make these, make the local images satisfy these kind of conditions. This is not a real proof, but I'm saying it's largely a computation using Tate's algorithm. And in our version, we need special conditions at the singular fibers. I gave an example here, but really I'm also there's a lot of assumptions on what kind of fibers there are and what properties they have to make this computation work. So I'm kind of pressing that, but that's there. Okay, so now here is the hint of the proof. I'm not going to go into the details because it's really miserable. We have the freedom to choose this set S of prime ideals and these open sets, these conditions, so that when we have this M and N coming from Chi's theorem, we look at the quotient, we get T is M over N. When I specialize the Selma group, this one Selma group has dimension 3. And it's very fussy, but see the paper, it's on my webpage now, it'll be on archive soon. The basic strategy is to think of how a successful Selma group computation would proceed and reverse engineer it. So I'm not starting with an elliptic curve. I'm choosing primes with strange conditions. And then later on, I find my elliptic curve, and all these strange conditions are used to make the Selma group computation work. So it's kind of, you're trying to make a successful Selma computation without the elliptic curve, and then you use T to make make it work. That, here's something, but um, you can take these sets UP small enough, you can actually assume that the local images you get don't depend on the choices of M and N, and hence also T for the primes and S. So you really can sort of take the set small enough so the local conditions don't depend on the elliptic curve at all. You just make all the choice to use your S and your local conditions independently, and then afterwards you feed an elliptic curve. And what else did I say? Oh, you take S large enough to make it a PID. So there's going to be a class number computation in there somewhere if you want to make it explicit. You're going to use Cherepanov to guarantee the existence of primes. There's some class field theory, all good stuff. There's some quadratic reciprocity for K. And in principle, you could make this work. If you really wanted to, you could follow the construction. And wherever Cherepanov says there's a prime, you find that prime, and you could actually do the construction. Okay, so this is a big general sketch, but it's sort of saying how you choose specializations for which this one Selma group is small as it can be, dimension 3 over F2. Now there's an issue, and that's because this is not exactly what we need to prove. We need to show both Selma groups are small. And in practice, if you're not careful and you make one Selma group small, the other one will be gigantic. So we have to kind of also make the other Selma group small, have the smallest dimension 3. And we handle this by using the following theorem of Castle's, which is using it's Castle, it's going to be using a parity and duality, a pairing duality. And it's that these two Selma groups, which I kind of said independently, their cardinalities are linked together. I look at the quotient of their cardinalities. It's the product over all places of K. And I have here the cardinality of that local condition I imposed at V divided by a half. For good primes away from 2, um, that term in the product is 1. So it is a finite product. And it's kind of a nice way of linking these two groups together. So what happens is when you choose your S and your sets U and guarantee one Selma group is small, you also at the same time have to make sure this fit in green holds, that this particular product is 1. And it's a little bit of a tightrope blocking thing, very balancing it. So in practice, what you're doing is when you're computing the Selma group, you have to make sure every relation defining the Selma group inside this non-zero square classes as an F2 vector space is actually needed. What happens if you have extra relations which aren't needed? That seems fine. That makes that Selma group what you want. But those extra relations will make this ratio of Selma groups less than 1, which will make this other Selma group bigger than you want. So you're kind of really doing a Selma group computation, but you're trying to be as efficient as you can be. And it turns out in this process, you're also, as an aside, you're forcing the root number to be 1, which is good. You're avoiding the half of the elliptic curves, which I believe should be rank 5. So you're in the right half. Okay. And now once we get the correct Selma group dimensions, we're done. We have rank is 4. Okay. So again, the summary is you have an elliptic curve. Its discriminant factors linearly. Use this theorem of chi to make special choices, and you have freedom on your choices. And you can use that freedom to actually make the choices so that the Selma groups are exactly what you want to get rank 4. That's the big structure. This is the hint of how you would produce one single T, one elliptic curve of rank 4. How do you produce infinitely many? Well, what you have is these constraints. And so you can take these constraints and you can shrink them small enough so that it rules out the T you already had. And then repeat the process and you'll get another T for which the elliptic curve ET has rank 4. And so you can just keep repeating and repeating and you'll get infinitely many elements of K for which the corresponding elliptic curve has rank 4. And now what's nice about this family I have is it's non-isotrivial. So its J invariant is a non-constant rational function. And in particular, it can only take a certain value. Well, yeah, its fibers are finite. So we have this infinite supply of T's, for which we have ET of rank 4. We plug them into this J function, and we get infinitely many different values. Okay, so what we have is, what this produces is infinitely many elliptic curves of rank 4 with different J invariants. And of course, the J invariant determines the elliptic curve up to isomorphism over K bar. So these are legitimately different elliptic curves we're constructing. And so maybe in contrast to a lot of work, in particular the Mazer, Rubin, and Koymans Pagano I mentioned earlier, there's really no twisting going on. A lot of work on ranks and a lot of elliptic curve things, you're thinking about twists because they're the most accessible family. And just to kind of, there's lots of reasons why, but one reason twists are great is because it makes the bad primes easy to understand. If I have an elliptic curve and I understand its bad primes, I twist it, it's easy to figure out what the bad primes are. I might be introducing new bad primes or changing them in some computational way, but understanding bad primes in a family of twists is straightforward. But in this non-isotrivial case, it's not so straightforward. And that's kind of what the green Tao generalization was used for, to make choices where I understood the bad primes. Yeah, I'm doing good. Some curves of rank greater than 4. So let's just see what goes wrong. If K is Q, we can consider all the plane cubics that pass through these 8 points. And they form a pencil of cubics. So all the cubics that go through this 8 points are of this shape. I have a parameter T. And it turns out they all intersect at a unique 9th rational point. And so I can take one of the points, and this cubic will define an elliptic curve over the function field Q adjoint T. So I have 9 points. One is the origin, so I have 8 points. And it turns out in this case, they are independent points, and I get a Mordell-Weil group of rank 8. In particular, any number fields, it's the same thing. So here's just the easy way I've made elliptic curves geometrically much higher rank than 4. So what goes wrong with the method? Well, first let's plug in t's. So we can just, like before, just take rational numbers, plug in t's. Now we get elliptic curves over Q. And this theorem of Silverman I mentioned earlier says that for all but finite many t, the geometric Mordell-Weil group maps into the Mordell-Weil group of our specialization. And so in particular, we're getting an infinite supply of elliptic curves of rank at least 8. And minimalist conjecture like before. Now, maybe now Bjorn has a point. I'm not convinced this is 50-50. I'd have to check. We should have rank equal 8, at least for some positive proportion of the time. So what's the challenge with showing it's 8? Why can't we compute the ranks? What goes wrong? The first thing that goes wrong, this mess, is understand the bad primes is miserable. So if you have a prime bigger than 11, and your E specialization has bad reduction at P, and suppose P doesn't divide the denominator of T, the rational number, then P divides the numerator of delta T, this rational number, where delta T is given by this giant polynomial of degree 10, and it's irreducible. And so if you're plugging numbers into that, rational numbers, and asking how does the numerator factor, that's a very hard question to do. I mean, for any particular T you can factor, but infinitely many T, it's conjectural. There's no way of understanding it at this point. But just think about plugging rational numbers in and understanding how it factors. I mean, integers in and figure out how it factors. It's a very hard thing to do. And so without knowing the bad primes, I can't compute Selma groups, and my upper bounds aren't going to give their actual rank. Again, in our earlier case, this factored linearly. Now you might say, oh, that's not a problem. Let's just increase the number field, and then it will factor into linear terms. But there are other issues that can happen. So for example, our curves we have here do not have 2 torsion points. And so the simple kind of Selma groups I computed don't work. You could instead work with the full 2 Selma groups, defined like before, except using the just multiplication by 2 isogeny of elliptic curve to itself. But that has issues. And basic issue is you're really any Selma group computation feels like it's going to use a cubic number field where you're looking at the number field for which 1, 2 torsion point is defined. And then when you're doing Selma group computations, it feels like you're going to need to know the class group and the unit group of this particular cubic. And this cubics are going to vary as you vary your T. And so trying to understand all this information with varying T seems maybe even harder than the problem I'm starting with. So that's why I picked the simplest kind of descent where I didn't have a number field that's varying in my parameter T. Okay, the final issue I have is that there are cases that seem like they should work, but don't. So everything seems okay. I have a 2 torsion point. The discriminant factors into linear terms. There's enough fibers and they have the conditions I want. But when I actually try to do it, the lower bounds and upper bounds for the rank don't agree. So at the beginning, I said, how you compute ranks is find lower bounds and upper bounds and hope they agree. In this case, the hope fails and they don't work, even for any choices. So here I just have an exact sequence, the rational points of ET mod 2 going into a Selma group with quotient kernel. And that is the 2 torsion of what's called the Tate-Chevarevich group. And so why you might not get lower bounds equal to upper bounds? Well, there's 2 possibilities, and I guess it could also be both. One is there's more points than you think. Your elliptic curve has higher rank than the minimalist conjecture predicts. And that could be true, but it seems unlikely you wouldn't be able to ever find that. And the more likely case, at least in the families I'm considering, is that Shaw, the 2 torsion of Shaw, is non-zero. And so it's this case where I have upper bounds and lower bounds, which don't agree. And as I'm considering infinitely many T, I don't really have the ability to actually check what the obstruction is. Are there more points I'm missing, or is it this Shaw is making my upper bound too big? In the example of the theorem I have, I avoid Shaw. The Tate-Chevarevich groups don't have the trivial 2 torsion in the families I consider. And I do this by choosing families with maximal rank. So in my example I gave earlier, I said geometrically rank has least the rank is at most 4, and then we saw it was actually 4. And this maximal rank condition somehow managed to sort of get rid of one-way extra elements of SHA could show up geometrically. Again, few minutes. So here's my theorem again. For any number field k an integer between 0 and 4, there are infinitely many elliptic curves over k of rank r. And I've given you the idea, and each r is just a different choice. They've found elliptic curves which have proper properties that I can actually run the method through and compute. And so we did r equals 4, and the other ones are very similar. Different kinds of fibers, different Tate algorithm computations, but very similar in construction. Each of, and 4 is as far as I got. I tried 5, I got stuck, and I've given up for now. Each of these curves is non-isotrivial and gives rise to an elliptic surface fibered over P1. And in particular, these ones are rational elliptic surfaces. They're birational to P2. And there's a construction similar to the rank 8 case. And it turns out that if you're looking at these rational elliptic surfaces with a 2 torsion point, which is what I want, the rank is always at most 4. So at least this class of elliptic curves I've been looking at, 4 is an upper bound. So I would need to look at this K3 surfaces instead if I would try to make the rank bigger. Challenge, can you make it bigger? Can you find families of curves that work for an integer r or at least 5? Most of the proof was just finding models that worked there. And you find one for 5. Waiting for time. Oh, good. Got a few minutes. So here I'm just a couple extra slides. So here's a related result that's recent. For any quadratic extension, L over K of number fields, there are infinitely many elliptic curves over K up to isomorphism for which the rank K points and L points, which is a bigger group, have the same rank, and it's 1. And so the proof was you fix an element of K that square root generates L. And if you have an elliptic curve, you have its quadratic twist, ED. And this theorem is equivalent to showing there are infinitely many elliptic curves over K for which rank of your curve is 1 and the rank of the twist by D is 0. And it's very similar to what I had before, but I'm using this particular model. And it's a little more complicated because you're doing 2 Selma group computations at the same time. But it's very much of the same spirit. Why this is interesting is, so this is the theorem again. The interest in the above theorem is that it generalizes the following 2 recent results, which both imply Hilbert-Tent problem for the ring of integers of a number field, that it has a negative answer. And so I think both of these theorems have been talked about in the seminar series, so maybe I won't say too much, but the first one of Koymans-Pagano is just that you're not saying what the rank is, but it's greater than 1, and it's only for special number fields and a particular quadratic extension. And the second theorem is you doing positive rank, and here you have abelian varieties instead of elliptic curves. And I have two more slides, and I'm done. Extra slides too. So you might ask about BSD. I have nothing useful to say about BSD. I just want to pose it as a question. Here's the L function. We have the L function defined in terms of the arithmetic. And on the left-hand side of the bottom, we have the analytic rank, the vanishing at 1 of a particular holomorphic function, and the algebraic rank on the right, the rank of our elliptic curve. BSD says they're the same. And so just an observation, there are only finitely many elliptic curves of rank at least 2 for which BSD is known to hold. For rank 0 and 1, we know lots of cases of BSD. Bargov and Skinner have more than 50% of most curves over Q satisfied BSD. But for rank at least 2, even greater, we only know finitely many cases where we just happen to have computed both sides. Now, what you can do is you can take rank 2 and 3, and in this talk, or at least suggested, you can construct elliptic curves with rank R, 2 or 3. It turns out, since you know the rank and you can compute the root number, you get the parity conjecture. At least BSD is true mod 2. And using work of Kolyvagin, you can actually get an inequality one way. And the challenge is, can you prove BSD for infinitely many of these E over Q? And at least I don't know how to do it, but at least now there's a supply, infinite supply of elliptic curves for which we know the right-hand side is 2 and 3. So you can maybe think about the left-hand side. And that's really all I want to say. So thank you very much.